All right, well, thank you very much, Dr. Griffin. Thank you. I'm very honored to speak here today. So, we're going to be talking about permutations in SN. And at least for now, I'd like to think about permutations in their one-line notation, right? So if I have a permutation W in Sn, I'll represent it as W1, W2 up to Wn. So this is a permutation in S7. We have the numbers between 1 and 7 that have been scrambled up into some order. 1 going to 4, 2 going to 2, 3 going to 3, and so on. And one of my kind of favorite questions in this field is, we have this scrambled up list of numbers, and how out of order is this list? How close is this list to being in order? And this is a question that has a number of different mathematical answers that lead to a lot of really interesting stuff. But what we're going to be doing today to answer this thing is we're going to look for increasing subsequences in this list of numbers. So for example, here we see this increasing subsequence. It doesn't have to be contiguous, of 4, 5, and 7. So this is an increasing subsequence of length 3, right? So you might wonder, can we find like a longer increasing subsequence? So can anyone see the increasing subsequences of length greater than 3?
2, 3,
Anyone?
6, 7.
2, 3, 2, 3, 6, 7, 2, 3, 5. Yeah, so here's one, like 2, 3, 5, 7. So this is an increasing subsequence of length 4. Anything of length 5? Participation? No, in fact. So I'm going to let LAS of W be the length of the longest increasing subsequence of a permutation W. And the idea is, if the longest increasing subsequence had length n, that would mean you just had the numbers between 1, 2, 3, up to n all in order. If the longest increasing subsequence had length 1, you'd be as out of order as possible. So this is some measure of the orderliness, right, of W. So as a combinatorialist, one thing that I at least nominally do is count, right? So we're going to be interested in not just counting permutations, but counting permutations by the length of their longest increasing subsequences. So I'm going to let A and K, where K runs between 1 and n, be the number of permutations in Sn whose longest increasing subsequence has length K. So let's kind of try to get a feel for what these numbers look like. We can start with the case of S3. So we have, of course, 6 permutations of the numbers between 1 and 3, and we're kind of dividing them up into buckets, right? There's this permutation, the reversal, 3, 2, 1, whose longest increasing subsequence is length 1. Then 1, 2, 3 has longest increasing subsequence of length 3, and the remaining 4 permutations have longest increasing subsequence of length 2. S4 is a little bit more interesting and only questionably visible. Sorry about that. So we get the numbers 1, and then it turns out there are 13 permutations in S4, and it's great. You can't actually check my work, it's too small. There are 13 permutations whose longest increasing subsequence is length 2, 9 with longest increasing subsequence of length 3, and 1 longest increasing subsequence of length 5. Oh, it's really scary. You can see an error. Oh no!
There's a 1, 2, 3.
There's a 1, 2, 3. Oh no!
1, 4, 2, 3.
Oh no! Oh, that's terrible. That's absolutely terrible. Let's advance. So let's assume that you ask your computer this question. I mean, I can't even do it accurately for n equals 4. N equals 5 would be a disaster. What you would get is sort of a triangle of numbers that look something like this, right? So I've made this kind of table of these A and K numbers. Here we see the 1, 4, 1. Here we see the 1, 13, 9, 1, and so on. And you might wonder, well, what sorts of patterns can you see, right? Well, first off, as I said, if I look at the permutations that are maximally out of order and in order, well, that corresponds to A and 1, A and n. So A and 1 and A and n, they're both 1, right? These rows all begin and end with 1. A little more interesting, so if you get bored with my talk, you can try to convince yourself of this. We see 1, 4, 9, 16, 25. A in n minus 1 is always n minus 1 quantity squared. So we see the integer squared going down there. What about this kind of second column here? A in 2 is, as it turns out, given by this number. So this is the nth Catalan number, 1 over n plus 1 times 2 n choose n minus 1. And you might wonder, what if we didn't take this second column? What if we took some other column? And this is a result of Ira Gessel, right? So what he basically did is he took kind of all of these numbers. So you're fixing k. In this case, we fixed 4. And you're looking at all of these numbers, a and k. And you're doing this trick, which is essentially looking at a generating function. You have this formal variable x. You sum over all n of this expression that's basically determined by a and k. We have this division by n factorial squared. And Gessel gave a determinantal formula for this formal power series involving Bessel functions. It's rather complicated, and in a colloquium talk, I think it would be bad manners to write it here. But these are pretty subtle numbers. They don't have a closed form. There is a summation formula, a sum of squares type formula involving partitions, but they're a little bit involved. So this is kind of one way you might try to understand these numbers. And another way is to imagine, what if we made this table go a lot further down? Well, you would have something that looks like this. So this is a histogram representation of the a and k numbers for n equals 65. So we have the 65 factorial permutations in S65, and here's how they break up into bins. And then these numbers, I mean, they still exist out here. They're just too insignificant to appear in this picture. And what we notice, we're seeing something distributional here. I mean, this is not a normal distribution. I've learned something since coming to Texas. This is an election in Denton. Ouch! No, I don't mean that in a bad way. It could be an election in Ann Arbor, where I'm from, or frankly, an election in most college towns. Maybe not College Station. So this is not a normal distribution. And as a matter of fact, there's a result of Hammersley and Vershik-Harov that as n tends to infinity, the average length, so the mean here, is something that looks a little bit like this. It's basically 2 times the square root of n. So this is always going to peak somewhere around root n. And there's a really famous result of Beck, Deft, and Johansson that relates the limiting shape of this distribution to an object in random matrix theory. So there's something called the Tracy-Whittem distribution that says something about the eigenvalues of a very large random matrix drawn from something called the GUE ensemble. And what these 3 authors did was they actually took that very complicated Gessel formula involving Bessel functions, and they used it to prove that a suitably renormalized version of this distribution converges in the limit of large n to Tracy-Whittem. Right? So this is a distribution that's important in random matrix theory. Okay, so I'm going to introduce a couple of new players to this story. We're going to have partitions. So a partition of n is just a weakly decreasing sequence of positive integers that add up to n. So 421, for example, is a partition of 7. And really, if you've kind of worked with these things before, the right way to look at partitions is shoving boxes in a corner. So we have these left justified boxes with rows of length 4, 2, and 1. So we have partitions, but we also have a standard tableau. And a standard Young tableau is just going to be a way of filling this partition with numbers 1, 2, 3, 4, up to however many boxes you have, that increase going down and increase going across. So this is a standard Young tableau of shape 4, 2, 1. And this is the most important bijection in all of algebraic combinatorics. I don't think I am saying all that much controversial there. So this is something called the Shenstedt correspondence, and what it is an explicit bijection from the symmetric group on n letters, Sn, to this thing, the disjoint union over all partitions of n of ordered pairs of standard Young tableau of that shape lambda. So I start with a permutation here's a permutation of size 7, and somehow, by some sort of magic, I am getting 2 standard Young tableaux with 7 boxes, so I have increase going down to the cross, and these 2 tableaux have to have the same shape. So the Schoenstedt correspondence is ordinarily presented with a sort of insertion and dumping algorithm, but we're going to describe it in a much more fun way in a little bit. But why was the Schoenstedt correspondence originally introduced? So it was originally introduced by Schoenstedt. And Schoenstedt was interested in this longest increasing subsequence problem, right? And Schoenstedt not only defined this bijection in his paper, but he proved that the number of boxes in the first row of, well, either P or Q, because they have the same shape, is always equal to the length of the longest increasing subsequence of your permutation W, right? So this is Schoenstedt's theorem. Really a remarkable paper. It's something like 12 pages long. And in terms of short but very impactful papers, I don't think you could do much better than this. By the way, this is Schoenstedt. So Craigie Schoenstedt, he changed his name to Ia, or I'm not entirely sure, and moved to rural Maine to pursue shamanic dancing and board game production. So he passed away only recently. But interesting fact. So the way I'm going to present Schoenstedt's bijection to you is really in this beautiful reformulation due to Viennot, Xavier Viennot. And it's the Viennot shadow formulation. And I'm kind of seeing now that my little graph paper may not be so visible to you guys, so I apologize for that. So, okay, can we dim the lights? Is that gonna make? Oh no! Yeah, we can shut off the lights. We can turn it back on. Yeah, I don't think it's gonna. Okay, low contrast, but that's okay. So we have our permutation in Sn, and I'm going to think about my permutation as a function from the integers between 1 and n to itself. So I have this graph where 1 is going to 4, 2 is going to 2, 3 is going to 3, 4 is going to 6, and so on. So I have the graph of this permutation, and I'm going to shine a light here. This spotlight will be located in San Diego, where the sun lives, right? And it's shining towards Maine, where Schoenstedt died. So Maine, I think, Sean is from Maine. It's a rather cloudy place often, right? So we're shining this spotlight, and we imagine that the points on the permutation, these black points, have a certain heft to them. They cast shadows. They cast L-shaped shadows. And these L-shaped shadows overlap in some interesting ways. Actually, some points in the permutation are completely obscured, right? These points, these 4 points inside here. And we're going to call this L-shaped boundary, right, between the shaded and unshaded regions, the first shadow line. So that's the first shadow line. Now, as you can see, we've actually lost some information here. We've lost the information of these 4 points in our permutation, so we will ask the points on the first shadow line to get out of there, and we'll shine the flashlight again, right? And now we have the second shadow line. The second shadow line, I guess, just looks like a single L in this case. We ask the single permutation point on the second shadow line to move. We have the third shadow line, and we shine again, we have the fourth shadow line. We've exhausted all of the points in our permutation. So we have this kind of iterated shine the spotlight construction. But what does that really do for us? Well, here we go. Slide slightly out of order. We record the coordinates of the vertical and horizontal rays when this construction is completed. And if you'll recall, this permutation mapped to this pair of standard Young tableaux under the Schoenstedt correspondence. And you see these coordinates for vertical rays, 1, 3, 4, 7, are the first numbers, are the numbers that appear inside the first row of Q, whereas the coordinates of the horizontal rays, 1, 3, 5, 7, are the numbers that appeared in the first row of P. Okay, so we got the first rows that way. But what about the remaining rows of these standard tableau? How do I get the 2, 6, 4, the 2, 5, 6, and so on? So what you do there is you take these shadow lines that look like these jagged things, and you look at the inner corners. So I call these things the shadow points. They're shown in red. And you can treat the shadow points as if they were the graph of some other function and apply the shadow construction again. If you apply the shadow construction again, you have, again, vertical rays, horizontal rays. They correspond to the second rows of P and Q. Shadow construction one more time, you get the third rows. Okay? So this is a way to look at really this Shinstead correspondence in a very graphical and very maybe insulting formulation. We live in the Northeast, I'm saying we live in a very shadow region. And one kind of cool thing about the shadow construction is it gives you a very nice way to prove Shinsted's theorem. So remember that the Shinstead result is that the length of the longest increasing subsequence of W is equal to the number of shadow lines. So in this case, I'm asserting that W has a longest increasing subsequence of length 4. And I'm going to claim that this is kind of immediate from this Vienno construction. And how does this work? Well, if you have an increasing subsequence of W, you can see, like for example, this increasing subsequence of length 4, every point on it blocks every subsequent point when I shine the light. So points in an increasing subsequence have to live on distinct shadow lines on the one hand. And on the other hand, if I imagine looking at the last shadow line, kind of marching down for infinity, marching across, marching down, marching across, marching down, marching across, marching down, I'm going to trace out an increasing subsequence of length equal to the number of shadow lines, right? If I kind of start here by a topology or something like that, I have to cross all 4 shadow lines to enter this region. Okay, so really nice way to see the Shinstead theorem that way. So everything that I talked about up until now has been known for about 50 years at least. But now I'm going to talk about something new, right? An algebraic model for this longest increasing subsequence statistic. But before I get to the new stuff, I guess I'll pause maybe for questions. You're a very docile audience. I think I intimidated you with the pointing stick. Okay. So what are we going to use for our algebraic model? We're going to use a certain kind of quotient ring. And this quotient ring will be referred to throughout the rest of the talk, so I'll be kind of writing it over here as well on the board. We'll have a set x sub n by n of n squared variables that I'll write in the matrix. So x1, 1, over to x1n, down to xn1, over to xnn, like that. And we're going to think about the polynomial ring in these variables over the complex numbers. So the next player, we're going to have an ideal I sub n living inside this polynomial ring, and I sub n will be generated by, well, 4 kinds of generators. So the first generator that you see fixes I, and we're going to just look at the sum of all variables in row I. So xi1 plus xi2 up through xin, so sum of all variables in row I, between 1 and n, but we also, to be fair, want to look at column sums. So we have x1j plus x2j plus xnj as j runs between 1 and n. So we have sums over rows, sums over columns, and now we'll have products And these products correspond to really attacking pairs of rooks on a chessboard. So we're going to have products of rooks in the same row, and also products of rooks in the same column. So here, 1 is going to be less than or equal to I prime, j prime, less than or equal to n. And I'm going to define Rn to be the quotient of my polynomial ring by this ideal In. So I have a certain kind of quotient ring, and what kind of structure does it carry? Well, the first thing to observe is that all of these generators are homogeneous. We have some linear generators and some quadratic generators. So if I take a polynomial ring, mod out by a homogeneous ideal, I get a graded ring. And not just that, my matrix of variables carries an action of a product of two symmetric groups. So I can permute the rows and permute the columns independently. And these generators, or the ideal generated by these generators, is stable under this action, right? This action is going to carry row sums to row sums, column sums to column sums, and attacking rook pairs to attacking rook pairs. So what I have is a graded Sn cross Sn module, but really, you're all far too docile, right? I think many audiences by now would just be screaming at me, why should we consider this ring? I just threw this ring at you, and we had this beautiful combinatorics of permutations before. You know, how can I justify that this ring has anything to do with Sn? Well, first off, the vector space dimension of this ring is infactorial, so that should be your first clue that there's something permutation E going on. Furthermore, if you look at the Hilbert series, so the graded dimension of this ring, what you get is the sum over permutations in Sn of Q, this is your little kind of grading tracker variable, to n minus the length of the longest increasing subsequence of that permutation. Right? So here's kind of another way to write that Hilbert series in terms of these A and K numbers. So somehow the Hilbert series has something to do with increasing subsequences. And we're going to make this connection a little bit stronger. And to do that, I have to just do a little bit of commutative algebra, or at least allude to a little bit of commutative algebra. So let's say that you have a term order, right, on monomials in a polynomial ring in some finite set of variables, say x1 up through xn. So a term order is just a total order on monomials that's a well order and interacts nicely with multiplication. One term order that you might want to consider for this talk is just the lexicographical order on monomials, right? The order you would put them in if they were in a dictionary. So if you have an ideal I inside a polynomial ring and in variables, perhaps in your abstract algebra class for undergraduates, you ask students to prove that this quotient can be viewed as a vector space, say over the complex numbers. And you ask them to prove that, and they smile happily, and they don't ask any more questions because, of course, you have the intimidation stick. But really, you should be asking questions, because what's a vector space really? If you want to operate with a vector space, really you want something like a basis, right? And if you take, an ideal that's not generated by, say, some subset of variables or some monomials or something like that, thinking about bases, right, from first principles of quotients like this is quite painful. But the miracle is, once you fix a term order and an ideal, there exists a unique standard monomial basis, vector space basis, of this quotient, right? So this is just a wonderful technique. It's a wonderful result in Grosvenor theory. So I encourage you all to read, for example, a Cox-Loci, Ideals, Varieties, and Algorithms. I'm seeing nods in the audience. It's just a beautiful book. But one thing to remark about this fact is, although you have this vector space basis that you always get, that you can always computationally find from Grosvenor theory, it's not always terrifically nice. And if you've never worked with these sorts of objects in the past, if you want to kind of hang your hat on something, think about row reducing a matrix. right? So I can think about a matrix as corresponding to an ideal by letting my generators be linear forms with coefficients, given by the things in my matrix. When I row reduce a matrix and then I look at where the pivots are, right? The pivot locations determine the standard monomial basis. And if I give you some, 17 by 37 matrix, right? Even if it has, some beautiful numerical patterns in its entries, row reduction is usually going to look absolutely terrible, right? There's no nice way to predict just by looking at it where the pivots are going to be, right? And the same goes, but even sort of more strongly for these standard monomial bases. So they're not always, and in fact not usually nice. But let's consider this standard monomial theory in the case of this quotient ring Rn. So we have a permutation W belonging to Sn, in this case n equals 7. And I'm going to associate to that permutation a monomial, and here's what I'm going to do. I'll do one iteration of the VNO shadow lines. So we have these 4 shadow lines. And I'm going to look at these interior points, these shadow points. So every interior shadow point has coordinates, ij, Cartesian coordinates. And I'll associate to that the variable xij. So we'll take that product. So we'll call this thing the shadow monomial of W. And by Shinsted's theorem, the degree of the shadow monomial, so 3 in this case, is complementary to the length of the longest increasing subsequence. So that's kind of a nice thing to think about, right? Every time you have a shadow point, it costs you a shadow line, right? And it can actually be proven that the set of shadow monomials is the standard monomial basis of Rn, right? So the crass way I have of saying this is that this is an ideal or a quotient ring that knows the Shinsted correspondence, right? Like as long as you take a lexicographical order with respect to some diagonal ordering of the variables like this, and take the standard monomial basis, what you get are these shadow points. And if you think about how the Shinsted correspondence works, it corresponds to iteration of this procedure on the shadow points of the shadow points, the shadow points of the shadow points, the shadow points, and so on. And given any collection of points, right, I can always form a corresponding ring that looks a lot like Rn, but only involves those variables xij corresponding to, say, the red points there. Okay, so this is sort of a happy example where the standard monomial theory of the ring is giving you something meaningful. And just to briefly talk about module structure, right? This ring is a graded Sn cross Sn module, as I said. If you're interested in the structure as an ungraded module, it is in fact, as a vector space, just C brackets Sn with the natural left and right actions of Sn coming from left and right multiplication. And if you're familiar with the representation theory of Sn, this theorem is kind of predictable, perhaps from what I said so far. If you look at a given degree d, the degree d part of Rn is isomorphic as an Sn cross Sn module to something that looks like this: a direct sum over partitions of n whose first part is size n minus d of the corresponding Sn Europe tensor itself. So this is really kind of for maybe the experts in the crowd. Okay, so I hope I've convinced you that this quotient ring Rn has some nice algebraic properties, but again, if you were a more aggressive audience, you might say that this all looks rather ad hoc. Where did Rn come from? And the answer is deformation theory, so orbit harmonics. So this is me yesterday in the Museum of Illusions in downtown Dallas. So deformation theory is orbit harmonics. It's this beautiful technique for producing quotient rings that often carry some very nice structure with regards to group actions. Okay, so that's me. So identify my head to a single point, and you have a picture that looks like this, right? So orbit harmonics is a machine, and like any good machine, it has an input and an output. So the input of orbit harmonics is a finite locus z in some affine space c to the n, and the output of orbit harmonics is a graded quotient ring R of Z of this polynomial ring in n variables. So we have our locus Z, and if you want a cartoon picture of orbit harmonics, we're taking my head, right? And I don't know if I would survive this. We're moving my head to this point in the middle. We're taking these 6 points and doing a linear flat deformation onto a subscheme supported at the origin of degree 6. Okay, so that's the cartoon, but what's really going on algebraically? Well, whenever I have a locus of points in an affine space, a very natural thing to do is look at the ideal of polynomials that vanish, right, on those points. So I go from Z to I of Z, I look at this quotient ring, I can identify that with the vector space of functions, right, on this finite set Z, Lagrange interpolation say. And I replace this ideal IZ with its associated gradient. So by definition, the associated gradient ideal is the ideal generated by all the top degree components of polynomials which are in my original ideal. Okay, so I go from this quotient, which is usually inhomogeneous, to a homogeneous quotient. So you know, I've learned a lot of kind of fancy algebra and fancy geometry doing this. You know, associated gradients, flat deformations, from going from combinatorics to algebra. But you know, even as you learn new things, you have to remember where you came from. So you ultimately came from combinatorics. So this deformation has partial memory. So it turns out that you always have a vector space isomorphism from C bracket Z to R of Z, and furthermore, not only do you have a vector space isomorphism, if you have any linear symmetry of the locus that you started out with, that linear symmetry is inherited, right, by this new graded quotient ring, and you have an isomorphism of modules. Yes?
What's a locus?
What's a locus? That's a great question. A locus is just a set of points for me. So a locus is literally a set of points. Now, you might be objecting, you know, what about things like varieties or zero sets of polynomials? For the case of finite loci, it doesn't actually matter.
Is it important that it's a non-reduced loci?
Is it important that it's a non-reduced locus? So you could do this for reduced loci, right? You would still actually always have an isomorphism of vector spaces and an isomorphism of modules if stable. But if you have a locus which is reduced like this, you have some kind of combinatorial interpretation of what this module might be. Okay. So other questions? So orbit harmonics, I just want to say, is everything, right? So many of the graded quotient rings that we love to work with in algebraic combinatorics can, in one way or another, be regarded as orbit harmonics quotients. If I take a regular orbit, right, for a reflection group W, I get something called the co-invariant ring. This is an example due to Costin, maybe the earliest use of orbit harmonics, perhaps. If I take the case of the symmetric group, and you imagine someone, I guess, living in one of the mirrors, right? So you have this orbit that's not full. What you get is the cohomology ring of a Springer fiber. This is work of Otto Springer, Tomasaki, Garcia Borghese. If you take some loci corresponding to combinatorial objects like ordered set partitions or more generally container fillings, you get these rings R and K that I thought up with Jim Haglund and Mark Shimizono, or more generally, rings that were studied by Sean Griffin, introduced by Sean Griffin in his PhD thesis at the University of Washington. You can get some very fancy quotient rings from this construction, like the Garcia-Heyman modules from Tableau loci, and you can get some quotient rings corresponding to objects in physics, the Donaldson-Thomas invariants of certain kinds of quivers, if your point locus consists of lattice points in something called a polytope of Bragg divisors. This is work of mine with Sutuari and Marcus Reinicke. So the overall idea is if you pick your locus in a smart way, you might get an interesting quotient ring out. Okay, so what are we going to do with Rn? So one thing that we try to convince our students of, perhaps in linear algebra, perhaps in abstract algebra, is that n by n matrices over a field form a vector space. And our students don't believe us; they think we're lying, but they do. We have faith at this point. So we have this vector space of n by n matrices, and we're going to think about the finite locus of permutation matrices. So I'm embedding my permutations according to their permutation matrices, And as a matter of fact, this quotient ring Rn is the orbit harmonics ring for the locus of permutation matrices. So for those of you that were thinking that Rn is ad hoc, maybe you think it's a little bit less ad hoc now. So this is where Rn came from, but this history was revisionist. This was a lie. Rn, I would love to say that Rn actually came from this, but it did not come from this construction historically. It actually came from cryptography. So there's something called the permuted kernel problem in cryptography, and I will give a vague statement of it. So let's say that you're working over a finite field Fq, Q being a prime power, and you think about an m by n matrix over Fq, and a vector in Fq to the n. So you have this matrix A, this vector V, and the matrix A and the vector V are both somehow known. And you know, in quotation marks, that there's a unique permutation W in Sn such that if I permute the entries of V according to W, A times this permuted vector WV is equal to 0. So the permuted vector is in the kernel. We have the permuted kernel problem. And the goal is to find W. And this no really is in quotation marks. You know, somehow you have to think very hard about the parameters m and n and v. Your matrix A and your vector V have to be random according to something that I don't really understand. And I think that in practice, when I was talking with cryptographers about this, no is in the sense that the computer says that, yeah, this usually works. So let's say that we want to study this permuted kernel problem from an algebraic point of view. So we have this basic equation, A, W acting on B equals 0. Our goal is to find W. Well, we'll introduce an n by n matrix of variables x. And I'm going to study the equation AXB equals 0. Right? That is this permuted kernel problem. So AXB equals 0. This is really asserting an equality of two vectors, right? I guess it's length m. And we have a collection of linear equations coming from this. So we have equations there. We also have equations that say that X has to be a permutation matrix. So this is kind of how you would study this problem from, say, a computational commutative algebra viewpoint. But this turns out to be rather hard, so we'll do something rather scientific. And we'll throw these things out. And maybe just as well, because I never quite understood what the conditions were on A and V, right, to make this actually work. So we have the conditions that X is a permutation matrix. And Pierre Barreau and Merton Rhoades conjectured something equivalent to the statement that the associated graded to the quotient ring that you get out of condition 2 alone has Hilbert series given by this thing, right? So they were looking at these algebraic objects. They had graded dimensions. They had these tables of numbers, much like the triangles of numbers I had at the beginning. They put these triangles of numbers into OEIS, the Online Encyclopedia of Integer Sequences, and they saw longest increasing subsequences. And they Googled my name. These are cryptographers working in France and Norway. And they said, pardon me, Professor Rhoades, are you interested in increasing subsequences and permutations? Is that something you care about? Yes. Here's an algebraic object that seems to have, really? So one way of interpreting the Hilbert series result is that they were actually right. Okay, so this is actually historically where this quotient ring came from. But the revisionist history leads to an interesting idea. So we can think about this ring R of Z as being the orbit harmonics ring for the locus of n by n permutation matrices, but why not study these orbit harmonics rings for other loci of matrices? And there's been a fair amount of work in this direction. So my student Jasper Liu studied this locus of R-colored permutation matrices. So you have these matrices that are a lot like permutation matrices, except now the non-zero entries are not all ones, but rather Rth roots of unity. Along with Jasper Liu, Yicheng Ma, and my new student Haizhi, I studied the case of involution permutation matrices. So these are permutation matrices that are invariant under transposition. Jasper and Hai, together with I alone, studied various loci of just rook placements. So now you have matrices that don't have to be square anymore, and you have these conditions that you just have a non-attacking set of rooks that need not be maximal. And along with Jae-Song Ho, I studied loci of contingency tables. So what's a contingency table? The idea is that you have a whole bunch of cities, so Denton, Dallas, Fort Worth, and Richardson, and they have to ship goods to some other cities, like, I don't know, El Paso. What are some other cities in Texas? Austin and College Station. And you have, this many, like 3 goods in Denton, 2 in here, 2 here, 1 there, and these cities have to receive this number of goods, and the contingency table is a way that this can be done. So along with Jay Song, I was able to kind of extend this theory to contingency tables. The algebra here, for some reason, was a little bit more involved. Now, let's talk about a conjecture, actually a rather difficult conjecture. So remember this picture from before, this distribution, this selection in Denton. So you might wonder, sort of what is the shape of this thing locally? So Bill Chen conjectured that this sequence of numbers, a(n)(1), a(n)(2), up through a(n)(n), is log concave. And what does that mean? It means that for any k, a(n)k squared is greater than or equal to a(n)k minus 1 times a(n)k plus 1. Yes?
Do we already know it's unimodal from some other reason?
Is the unimodality open? In fact, I'm not aware of a proof of unimodality. Yeah. So unimodality might still be open, and log concavity is certainly open. And I mention log concavity in part because, as you may know, Jimmy Ha won the Fields Medal, and he won the Fields Medal in part because of his work on log concavity of, say, certain sequences of numbers arising from matroids. So log concavity is a very hot topic in combinatorics these days, and this is an open log concavity conjecture, which would be awesome to prove. And well, one thing you can do if you can't prove a conjecture is make it harder, right? So you can think about equivariant log concavity with a group action in the mix. So let's say that you have a group G and 2 G modules V and W. Well, G acts on the tensor product of these vector spaces, V tensor W, by this rule, this diagonal action rule. And we're going to define a sequence V1 up through Vn of G modules to be G log concave, or equivariantly log concave, if for all I, we have a G module injection from, well, the I minus first thing tensor the I plus first thing to the ith thing tensor the ith thing. So if you were to take dimensions on either side, what you would conclude is that the sequence of dimensions of these vector spaces is a log concave sequence. So this is a stronger property. Right, so relatively straightforward to state, but if you know the representation theory of the group Sn, you should be quaking with fear, because what I'm really doing here is something called Kronecker product of Sn representations. And this problem of taking a Kronecker product of 2 irreducible Sn representations and expanding in terms of Sn representations, that's just notoriously difficult. So something that's easy to define, but maybe difficult to understand. Okay, so we have this Sn cross Sn module, Rn, right, that quotient ring with respect to row and column permutation of the variables. And it breaks up according to degrees. So we have Rn0, direct sum Rn1, Rn2, up through Rn in minus 1. And the conjecture that I have is that this sequence of representations, Rn0, Rn1, up through Rn in minus 1, is in fact Sn cross Sn log concave. So if you could prove this conjecture, you would have proven Chen's conjecture, right, just by taking dimensions. This has been verified for n up to 15, so I have some confidence that it might actually be true. And somehow it doesn't look all that bad. I mean, this is not maybe the most complicated quotient ring in the world. And all we're doing really is we're saying, okay, for each I, I want to take something of degree I, something of I minus 1, something of degree I plus 1, produce 2 things of degree I in such a way that I have an injection, right? And I respect my ideal, but I do not know how to do this. It may be very difficult. And in general, I'd like to say that many of the quotient rings that you get from these kinds of constructions, right, thinking about other matrix loci, tend to exhibit log concavity or equivariant log concavity when you have group actions. And I think this might be an interesting place to look, right, for log concavity, equivariant log concavity conjectures, and maybe by the time I'm dead, some of these conjectures will have been proven. And with that, thank you all for listening.
More questions?
Yeah.
Are you also going to change your name and take on shamanic dancing?
Am I going to change my name? I haven't proven a good enough result yet. But I'd have to prove something of the magnitude of Schoenstatt correspondence and Schoenstadt's theorem before I can do that.
So once you prove the G on log concavity.
Yeah, that's right. So once I've proven this conjecture, please look for me on an island in Maine.
Do you have a conjecture for like a Lefschetz element for this ring?
Is there a conjectural Lefschetz element for this ring? So if we kind of go back to this picture, right, the Hilbert series is obtained by basically taking this and reflecting, right? So we conjecture that this thing is top-heavy, but we don't really have a conjectural Lefschetz element. I mean, the natural thing that you might try to do, especially if you wanted something as in process variant, would be like summing over variables. But that's going to die because of your ideal, right?
Well, what if you like put distinct
Coefficients,
distinct
yeah.
coefficients on each one or something?
Yeah. So I mean, Lefschetz elements, it's again sort of a hay in a haystack problem.
Yeah.
Right. If I have a linear map between a vector from a vector space of dimension 17 to a vector space of dimension 34, if I give you that 17 by 34 matrix, does it have full rank? Probably. If I throw in random numbers there, probably. But on the other hand, if you say, well, this number has to be 0.7, this has to be pi over 3, this has to be 17, is that going to have full rank? Yeah, that's quite painful. So no conjectural sort of, I guess this might be called a weak Lefschetz element or something like that. So nothing like that. So good question. Yes?
Is there any sort of relationship between certain matrix loci and the geometric properties of the schemes of the graded rings you're sort of cooking up, like smoothness or some sort of other nice algebraic properties that if you pick a certain nice matrix loci?
Yeah. So these loci are, well, they're non-reduced and zero-dimensional, so they're never going to be smooth, right? So I guess I would say that this isomorphism is also almost never an isomorphism of rings, because if you start with a reduced locus here, you have a reduced quotient ring here, whereas this is not reduced. So what you're getting really is a flat deformation, a flat linear deformation of this locus onto the origin. And you can use that fact to see, or you can use maybe more hands-on methods to see that you have a vector space isomorphism or a module isomorphism in the presence of linear symmetry. Right, so were you kind of wondering about other geometric properties, or?
Yeah, or just some of the other, I guess, other sort of matrix loci that you picked up.
Yeah. So is there some way that you can predict, for example, we have a Hilbert series associated to each of these matrix loci. Is there a way just to look at the locus of matrices and predict the Hilbert series? So part of the magic of orbit harmonics is it's often quite subtle to guess the Hilbert series from this embedding. So let me kind of try to convince you of this. So we have permutations, right, in SN, but there are a couple of ways or multiple ways you can embed permutations as points. You can embed them as permutation matrices. And I talked today about how you get longest increasing subsequence-like statistics out of that. But you can also embed permutations just according to their one-line notation, right? And if you were to take that embedding of n length n permutations inside C to the n, what you would instead get is a Hilbert series, which is the Q analog of n factorial, so the generating function for permutations according to the inversion statistic, counting out of order pairs. So if you're geometrically inclined, what you're getting in terms of a quotient ring is the cohomology of the full flat variety of type A. So you get really a very different algebraic object by choosing a different embedding, right? And it's not usually so obvious looking at the embedding what sorts of Hilbert series you're going to get.
Any other questions? If not, let's thank our speaker again.